Hey guys, welcome back to chapter 14. In this video, we're going to start to introduce strong acids, strong bases, weak bases, and just get to know a little bit more about solving these problems. So the first thing I want to share with you are strong acids. So there's going to be 5 strong acids that you just need to memorize. So these, I kind of jokingly call them the big 5. If a problem has one of these 5 in it, it's a strong acid problem. If it is not one of the big 5, then it's going to be a weak acid problem. So here's the big 5. The big 5 are going to be hydrochloric acid, hydrobromic acid, hydroiodic acid. So those halogens right there. The other 2 that you'll need to memorize are nitric acid and sulfuric acid. Chloric, perchloric, also strong acids, but it's not going to be something that I ask you to have like memorized. The big 5 are the most important, so we'll stick with those 5. Okay. If it is a strong acid, what is that going to look like, right? So any of these, I could pick any of these 5, and the same is going to be true. If I had a chemical reaction with one of these big 5 strong acids, let's take nitric acid. So if I had HNO3, and I were to drop it into water or react it with whatever, that's going to be a complete dissociation. So every single one of those acid molecules is going to dissociate into the hydrogen ion and nitrate. So one-sided arrow, we see that all the way down, complete dissociation. Okay. If it is not one of these big 5, it will be a weak acid. Weak acids partially dissociate. This is going to be an equilibrium problem. Okay. So let's take a look at an example. So hydrofluoric acid is an example of a weak acid. When we drop hydrofluoric acid into water, part of it will dissociate into the fluorine ion, and then that hydronium. Part of it will stay together as hydrofluoric acid. So some hydronium will be created, but not a lot, not very much. To solve these problems, it's going to be an equilibrium problem. Okay? So to solve these problems, we're going to have an equilibrium constant K for this reaction. So just as we saw in the last chapter, it's going to be concentration of products over the concentration of reactants. So in this particular scenario, our products are going to be a fluorine ion and that hydronium. For our reactants, we got to be careful here. For our reactants, we're going to have the hydrofluoric acid, and that's it. Now, why would I not include water in this equation? Water is a liquid, right? Solids and liquids don't get included in the equilibrium reaction. Water is a liquid, so we don't include it. One other little switch you're going to see here. So for the equilibrium chapter, we saw K was just K, or it might have had a C down here for concentration. Now that we're in the acid-base chapter, we need to kind of tell the viewer a little bit more. We need to kind of be a little bit more explicit. So when we're dealing with weak acids, that K value will have a subscript A, and that A indicates that this was an acid. So our Ka value, concentration of products over concentration of reactants. This constant, the equilibrium constant, that's what we called it in the last chapter. In this chapter, we're going to call it the acid ionization constant, or Ka value, okay? It's going to help us to determine the relative strength of these weak acids. So some weak acids dissociate more than others. Some weak acids barely dissociate at all. So there's going to be kind of a continuum for these. So let's just get to know this Ka value a little bit better. What does it tell us? Well, if the Ka value is significantly larger than 1, this would be probably more of an indication of a strong acid. So if we looked at an equilibrium constant that was something like, 120, that would probably indicate that it's a strong acid, okay? So remember, if our Ka is products over reactants, having a very big number on top means that forward reaction is favored, and that would give us a value over 1. For Ka values that are significantly less than 1, that's where we find our weak acids. So if we have something that's less than 1, we would have, again, a bigger number on the bottom. So it kind of reactant favored in that case, and that would indicate a weak acid. Not a lot of it dissociates. So here's just a chart of some common weak acids, and that gives the Ka value. So again, it's a constant. It's something that's going to be given to you on a test. But we see the Ka values. So up here for chlorus, we see 1.1 times 10 to the negative 2. So that would probably be like the strongest of the weak acids, right? And then we come down here, we find acetic acid, so it's going to be one of the weaker ones. And then lastly, we've got like our phenol, has Ka value of 1.3 times 10 to the negative 10. That's a very, very small number, which indicates that most of this stays together. Only very, very little of it would break apart. Okay. So let's look at a problem. Let's do a little bit of practice together. How might I start asking questions? What might that look like? How can I apply what I know to this information? So here's a problem that we're going to work together. So I want you guys to write a balanced chemical equation for the dissociation of acetic acid in water. So acetic acid plus water, write the balanced equation. And then once you have the balanced equation on the paper, go ahead and write the Ka equation for that. You can pause the video if you want to try to work it on your own. I'll catch up to you in just a moment. All right, so first thing we're going to do is write our balanced equation. So we've got acetic acid, and we're going to put that into water. I told you acetic acid is a weak acid, so it's going to be a double-sided arrow. Acetic acid, that is going to be our proton donor. So this hydrogen right here is going to be donated. How do I know it's that one and not one of these? I just know. But typically for acids, the hydrogen that gets protonated or donated is going to be written in the front here. Okay. So acetic acid is our proton donor, so what's going to be left is C2H3O2. And if it loses that positively charged particle, it's going to be left with a negative charge. All right, water in this case is going to be our base. He's going to be our proton acceptor. So he had two hydrogens. Now he has 3. With that addition of a positively charged particle, he's going to have that positive charge. Now we want to write the Ka equation for this. So Ka equals concentration of products over concentration of reactants. Both of our products are aqueous, so they're dissolved in water. We will include them. It's on the outside, on the inside. So there's our products. And then for reactants, water is a liquid. So the only thing that's going to be on the bottom here is the acetic acid. So that's it. I want you guys to get comfortable with being able to write chemical equations when we dissolve things in water. I also want to get you guys comfortable with writing those Ka equations. It's the same skill set as the previous chapter. Sometimes when I do acids and bases, though, wires start to get crossed, things get a little bit challenging. So make sure you practice this skill. I hope you guys found this helpful.